Dear students, today's topic is on uninformed search strategies from unit number 1. Dear students, before going to today's topic, let us recap about previous session for 1 minute. A problem consists of 4 parts. They are initial state, set of actions, goal test function and path cost function. An environment of a problem is called as state space. A path to a state space from initial state to goal state is called as solution. Search tree algorithms are used to solve any kind of problems. Previously, we have already discussed about several toy problems. We are going to apply those problems on search tree algorithms. A node is a data structure used to represent search tree. Collection of that nodes have been generated but not yet expanded is called as fringe. In today's discussion, we are going to discuss more about fringe. Search algorithms are judged on the basis of completeness, optimality, time and space complexity. And today's topic is uninformed search, also called as blind search, where we don't have any information about the length or cost of a path to a solution. That means no additional information about states beyond that provided in the problem definition. That means what we have to do is to generate successors and distinguish a goal state from non-goal state. Today we are going to discuss about two search tree algorithms, breadth first search and depth first search. Let us discuss about basic search algorithm which uses fringe as a data structure. Let us define fringe. A fringe is a data structure that contains nodes that have been generated but not yet expanded. Generally, fringe uses Q as a data structure where it uses FIFO as an operation to find out the goal state. Let's start our discussion with a basic search algorithm. Let fringe be a list containing the initial state. That means in our Romanian example, the initial state we have considered as Arad and we have to reach Bucharest as a goal state. Let us continue the steps to find out two conditions, either a goal state or failure state. If fringe is empty, that means we have not find the goal state, which returns failure. If not, remove the first element from the fringe. That means remove the first node using FIFO operation. If that node is a goal state, then return the path from initial state to the current node. Else, generate all successors of the node. In our Romanian example, in Arad is not a goal state, then we have generated three successors. They are in Sibiu, in Timosira and in Jared. Merge all the newly generated nodes into a fringe. Continue this process until to get the goal state. We are going to use the basic search algorithm in breadth first search and depth first search algorithms. Let us consider an example of state space graph where A is a initial node and G is a goal node, where we have to list all possible paths and try to eliminate cycles from the paths. The resultant state space graph has to be converted to search tree. The left side diagram shows the state space graph and the right side diagram shows the search tree where A is a initial node and G is a goal node. We have to move from initial state to goal state, from state to state by having actions. A is a root node and G, H, E are called as leaf nodes. A is an ancestor for B and C. D and E are descendants for B. The branch factor is every node having one or more children. So the maximum number of children is B equal to 3. The complete path is A, B, D, C, G is called as complete path, and A, B, D or A, B, E is called as partial path. We are going to expand nodes in closed nodes.
Breadth first search, in short BFS, is a simple strategy in which the root node is expanded first, then all the successors of the root node are expanded next, then their successors and so on till we reach the goal node. If all the successors are completed, still if we did not get the goal node, that is a failure. In general, all the nodes are expanded at a given depth in the search tree before any nodes at the next level are expanded. BFS can be implemented using FIFO queue, first in first out queue, assuming that all the nodes that are visited first will be expanded first. FIFO queue puts all the newly generated successors at the end of the queue, which means the shallow nodes or leaf nodes are expanded before deeper nodes. Let us discuss using an algorithm.
Breadth first search or BFS algorithm is exactly same as our basic search algorithm, but the change is generate all successors of a node and expand shallowest node first. Finally, add generated nodes to the back of fringe. This is the change. Let us discuss BFS algorithm with an example. Let us discuss BFS algorithm with an example. In this example, we have considered the initial state is A. We have to move until we reach the goal state. Goal state we have considered it as G. Initially, fringe consists of initial node A. Check whether the node A is a goal state. If not, expand the initial node A. Its successors are B and C. Now remove A from fringe and add B and C nodes into the fringe. Check for B is a goal node. If not, expand its successors. Its successors are D and E. Remove B from fringe and add D and E nodes into the back of fringe. Now fringe contains C, D, E nodes. Check for C is a goal node. If not, expand its successors. Its successors are D and G. Remove C from fringe and add D and G to the back of fringe. Now fringe contains DE, DG nodes. Check for the node D is a goal node. If not, expand its successors. Its successors are C and F. Remove D from fringe, add C and F to the back of fringe. Now fringe contains EDGCF. Now check for D. Is it a goal node? If not,
expand its successors. Its successors are B and F. Now remove D from fringe, add B and F to the back of fringe. Now the next node is G. G is a goal node where we will stop our navigation and finally print as G as goal node. Evaluation criteria for BFS. BFS is complete if the shallowest goal node is at finite depth D. BFS will eventually find it after expanding all shallower nodes. So we can call BFS as complete. Second property is optimal. The shallowest goal node is not necessarily the optimal node in BFS. Technically, BFS is optimal when all the actions have the same cost. It may not be possible in real conditions. A complete search tree of depth D where each non-leaf node has B children and it has a total of B plus B to the power 2 plus B to the power 3 plus and so on. Finally, the worst case order of B to the power D plus 1 nodes the BFS contains. The advantage is find the path of minimal length to the goal. Disadvantage is which requires generation and storage of tree whose size is in exponential. The algorithm for DFS is exactly same as of our basic search algorithm, but only change is expanding the deepest node first and add all the generated nodes to the front of fringe. This statement is change. Remaining statements are common with the basic search algorithm. Let us discuss with an example. Let us discuss an example with the DFS algorithm. Our initial state is A and our final state is G. Now let us apply DFS. Initially, the fringe contains initial state A. Check for the initial state A is goal. If the initial state is not a goal state, then expand all its successors. Its successors are B and C. Now remove A from fringe, add B and C into a fringe. Check for whether B is a goal node. If not, expand its successors. Its successors of B are D and E. Now add the expanded successors to the front of fringe. Now D and E will be added to the front of fringe by removing node B. Now check for whether D is a goal node. If D is not a goal node, and expand its successors. Its successors are C and F. Now remove D from fringe, add C and F to the front of fringe. Now fringe contains C, F, E, C. Now check for C is a goal node. If C is not a goal node, expand its successors. Its successors of C is G. Now remove C from fringe, add G to the fringe. Now G is a goal node. We identified the goal at depth 4 using DFS. DFS is always expands the deepest nodes in the current fringe of the search tree. The search proceeds immediately to the deepest level of the search tree where the nodes have no successors. DFS uses LIFO as data structure, that means stack. DFS has very modest memory requirements. It needs to store only a single path from root node to leaf nodes. For a state space with branching factor B and maximum depth of M, the DFS requires the storage of only B multiplied by M plus 1 nodes. The references of this lecture is Artificial Intelligence, a Modern Approach textbook by Stuart Russell and Peter Norving, second edition. And I have followed the lecture series on Artificial Intelligence by Professor Sudeshna Sarkar, Department of CSE from IIT Kharagpur from NPTEL.